where we were, I was trying to explain some formalism of Hecke operators. And I said the following. Whenever you have a finite set I, and you have a representation V and a sheaf F on X to the I, then you're getting some kind of functor from sheaves on bun G to sheaves on bun G. So essentially what you should think is that I map first from bun G to bun G times X to the I, which is sort of these pointwise Hecke functors. Then my F gives me some kind of like measure on X to the I. Maybe it's like a delta at just a point on X to the I. And then I'm sort of integrating along that measure in order to get a functor from bun G to bun G. So for instance, if it were a delta on some X to the I, so on some I tuple of points, this would just be the composition in whatever order of the Hecke functors at those points. And generally, you should think of it as some kind of integral along the curve weighted by this F. Okay, so now I want to give a kind of universal source for that construction. So this is going to be a certain category. It's kind of abstract. It's called rep G check Ron. So Ron space means I allow finite sets within my curve, and I allow points to sort of vary the way they do, like in X squared, like two different points can degenerate into one point along the diagonal. But I allow that for all I tuples unbounded. And the sort of universal source, so that's what it stands for, but it's a definition. So it's going to be something which is called colimit over twisted arrows category of finite sets of sheaves on, I'm going to get the formula right, X to the I tensor G check to the J. So this is a colimit in the world of DG categories that have all colimits, and it's something abstract. I said it would be abstract. Look, it's abstract. But let me tell you what this means. So what I'm gonna so the claim is that this is some kind of symmetric monoidal category and it acts on these sheaves on bun G. So first of all, for every I have a certain functor. We call it assertion sub I from sheaves on X to the I. Again, I might be switching these basic, the order of these two in the future, and I apologize. So for every finite set I have some construction that takes a sheaf on X to the I and a representation, an I tuple of representations, and produces an object here. And then there are some basic relations that have to do with maps between finite sets. So if I have kind of basically the assertion is that whenever I have some diagram, some map of finite sets from I to J, this is going to give rise to a commutative diagram. Like sheaves on X to the J, tensor with rep G check to the I. And I can map this to sheaves on X to the J, tensor with rep G check to the J. So this will be sort of the identity on the first factor. And it'll be, so I have my map from I to J, I can sort of tensor along the fibers of these maps, which is also whenever the fiber is empty, I just stick in the trivial representation. So I'm writing that as mult on the second factor. It's using this map from I to J. And then I can apply my insertion for J here to get to rep G check run. Or I can sort of use my map I to J to get a diagonal map from X to the J to X to the I. So in some sense, like a point of X to the J is a map from J to X, and I just compose with the map from I to J to X. And so this is going to map sort of some diagonal sort of map to sheaves on x to the I, tensor with rep g check to the I, and then I can apply this insertion here. And then there's going to be sort of plus some higher compatibilities that if you had a tuple of maps, all of the commutative diagrams you could build would coherently commute. So commutativity in higher category theory is really a structure. So I say it commutes, but that's really an extra structure. And what I want is some huge diagrams all commute simultaneously. So that's what this short formula encodes. I guess I wrote kind of very concretely a couple examples. Maybe I'll just write one for the sake of time. So if this is my I and this is my J, the kind of thing that this is saying is that if I take sheaves on X, so if I take a pair of representations, one thing I could do, a pair of representations and a, let's say, for instance, a point on X or a sheaf on X. One thing I could do is I could tensor those representations. Or the other thing I could do is consider this as the kind of data I would see for the tensor square, and the assertion is that this diagram commutes. So this is kind of saying that if you take two representations and then your sheaf is just like, for instance, a skyscraper sheaf on the diagonal, the corresponding like Hecke functor from bun-G to bun-G is going to be the same as the one you got by just tensoring those two representations and thinking of them as living at that single point. So it's encoding that kind of compatibility. The other thing it's saying is that if you insert the trivial so this is a classic map of finite sets. The other kind of classic map of finite sets is like the empty set mapping to a singleton. And that's going to tell you that if you sort of insert the trivial representation at some auxiliary point, kind of does nothing in a suitable sense. Okay. So the sort of the form of the Hecke action I want is that this rep g check run is going to act on sheaves on bun-G, and it really sort of it acts by kernels, by like functors given by kernels, in the sense we talked about before. So what that really kind of means is that I have a canonical functor from here to sheaves on bun-G times bun-G, and this is it's a sort of monoidal functor. So this, again, I was saying you can sort of think of it as like being like matrices somehow. This sheaves on y times y, and this has a sort of canonical, people call convolution product on it using upper star and lower Schrieg functors. And this will be monoidal. And I'm going to call this by V maps to K sub V. So some object here maps to some given kernel here. And this is the kind of abstract way I want to think about the what the Hecke action gives me. Okay, so and let me just put as an example. So somehow this V is I'll call it like the trivial representation. It's sort of what you got from when your finite set was the empty set, and then you get a copy of vect and you just insert. This is the tensor unit on this category. Then this K sub V is going to go to somehow the identity here, which is delta lower Schrieg of the constant sheaf on bun-G. So this is, so to say, the matrix with ones along the diagonal in that dictionary.
I have a question.
Yeah.
Here, so the Hecke operators we saw earlier were valued had values in bun-G cross X to the I sometimes.
Mm-hmm.
So where is that X part?
So that X part comes up in the fact that this rep gcheck run category, so it is actually slightly lossy and it causes a technical issue. There are many technical issues in these papers, and this is one of them. But what's happening is this rep gcheck run, what I'm allowed, like a classic object is you take an I tuple of representations and a sheaf on X to the I. And what you think of the Hecke functor that you did here is like you applied that sort of universal one that you just said. Then I take my sheaf on X to the I and I kind of use that to integrate along the X to the I factor. So it's not quite true that from this data you can recover the sort of Hecke functor that I said before. It's like slightly lossy, but it's not that bad in practice.
Thank you.
Yeah, so in some sense, I moved that X to the I from the right to the left. So before it was like, you can imagine, like if this were a nicer sheaf theory or something, where'd it go? You could think of this as sort of a functor from like rep gcheck to the I tensor with these sheaves on bun G to here. And ideally, this would be a sort of tensor product on the right, and you could try moving the right factor over to the left. That's kind of heuristically what's happening by some kind of self-duality of sheaves. So now a kind of key definition for us is that the functor, the Stuka functor from rep gcheck run to vect is what should I say? The composition so like I guess for the previous discussion about Hecke functors, everything was purely geometric. But now I'm going to assume again I'm in the arithmetic situation, and I need to use Frobenius. So what I'll do is I'll take this rep gcheck run. It maps to sheaves on bun G times bun G. I'll pull back along the Frobenius on one of the factors. And then finally, I'll apply this geometric trace. So this is my functor.
Sound disappeared immediately.
Yes.
Yes.
All right. How's this?
Yep.
Okay, so this is just purely motivated by that discussion earlier. So I'm just saying I get some operator. I'm going to pull it back along the Frobenius, just like, and then take its geometric trace. So this is rigged so that the geometric trace, that Stuka, this trivial object, for these compactly supported functions on G of FQ. And let me now say the relationship to kind of usual Stukas. So, like, if you look in, I see there's a message in the chat. Universality for the functors. I don't know what that means, but maybe we can talk about it during the Q&A session. So if you look in like anyone's paper but ours, this is not what Stukas are. So so let me say what usual Stukas are. So fix a finite set I. Then I'm going to define a functor. Well, maybe I'll define a sort of true Stuka functor from rep gcheck to the I to sheaves on x to the I as sending v to, like, I'm going to write this a little bit informally, but geometric trace tensor with the identity of so the identity times Frobenius times identity upper star of this case of V, not plane V. So what does this mean? So I wrote this in a kind of complicated way. So what this really just means is you take this case of V, that's a sheaf on, now, like we just discussed, bun G times x to the I. And I pull it back along the Frobenius, let's say along the second bun G factor, just to match the formula I just wrote. And then I again have a sheaf on bun G times x to the I. And then I'm going to do that trace construction sort of just along the first two factors. So really what this means is I take the identity for this x to the I take the diagonal for bun G, I pull back along this, and then I apply projection to the second factor. So this is some sheaf on x to the I, and this is what is called, like, somehow usual cohomology of Stuka's. It's something, this is the nature of it. It takes an I tuple of representations and produces a sheaf on x to the I.
I think it is a little bit hard to read. Would you mind writing the same thing a little bit bigger? What does it say there? So the first bracket, I think I can read, but the second one, what does it say?
Okay, I'll write it differently. So I take case of V, which is a sheaf on bun G times x to the I. Oh, I see that I didn't write any bigger. Let's try that again. So I have this case of V, the sheaf on bun G times x to the I. So I'll just slightly simplify the formula of what I wrote. So I'll take the graph of the Frobenius for bun G here, times the identity on x to the I, pull back along here. This maps to sheaves on bun G times x to the I, and then I push forward down to sheaves on x to the I.
Okay, thank you.
So if you look in literature, maybe up to some base change or something like this, this is the standard formula. This is the standard kind of thing for what Stukas give you. Bunch of representations gives you a sheaf on x to the I. It's this sheaf. And here I'm sort of, what I wrote over here is pull back along Frobenius and then apply this trace, which is a little bit how I want to think about it, as it says in 2 steps. And maybe I'll put an I here in the notation. Okay, so on the other hand, let's say given a functor f from rep g check run to vector spaces, I obtain functors. So I want to explain the relationship between my construction, which was a functor Stuka from here, to the previous construction, which is this kind of data. Obtain functors for every I that I'll call f sub I. And these are going to go from rep g check to the I to sheaves on x to the I. And they're going to be characterized by the following formula. For f a sheaf on x to the I, And I guess let's say V representation on G check to the I. So one thing I can do is I can take F of this F, sorry, insert I, this F box times V. Or the other thing I can do is I can take cohomology on X to the I, F, tensor with this F sub I of V. So in other words, what I'm going to do is imagine I fix this factor V for a moment, this representation, which of course will be later allowed to vary. So I get two kinds of data out of this. One is I get a sheaf on X to the I. The other thing is I get a functor from sheaves on X to the I to vect. Namely, I can sort of pair the two. If I have a sheaf on X to the I can pair it with my representation to get an object of this category and then apply my functor F. It turns out that every functor, turns out it's just like the way Verdier duality works. Every functor and like it's like a representability theorem. It's like an int category thing. That every functor from sheaves on X to the I has this form for some object. It's always given by tensoring in this Schriek sense with some object and then taking cohomology. So these are the kinds of data I'm going to relate. And there's a...
Can you move the left?
What was it?
Can you move it so it's visible?
Yes. Sorry, the transition is always not quite right. So an exercise, which is just sort of base change and so on, is that, so I can apply this in particular to my sort of Stuka functor. And the exercise will say that cohomology of X to the I with coefficients in, this is for every F sheaf on X to the I and V representation of G check to the I. One thing I can do is take the Stuka true of V. I can star tensor with F, which is slightly annoying, but kind of makes sense because these Stukas play well with star tensoring by definition. Like everything about these Stukas is upper star, lower Schriek. And this is going to be the same as the cohomology of X to the I with coefficients in this is an I, this Stuka I, sort of fake or whatever. This formal version I said, tensor Schriek with F, which declares sort of Stuka of insert I of F box times V. So that's the compatibility between the two constructions. So now I want to appeal to Jouet's theorem for a moment and say that Stuka true of I of V actually is not arbitrary. It's actually a Lees sheaf on X to the I in the sense I defined before. So all of its cohomologies are, so to say, local systems on X to the I. And then it follows. So this business about star tensoring versus Schriek tensoring, it's all kind of seems abstract, but really when you're just dealing with local systems, when one of the factors is a local system, I should say, they just differ by shifts, essentially because we're on a smooth variety. So to say the constant sheaf and the dualizing sheaf differ by a shift, and one of them is the unit for like the star tensor. The constant sheaf is the unit here, and the dualizing sheaf is the unit here. So you can, somehow go back and forth by tensoring with the dualizing sheaf in its inverse.
So these equalities are up to homological sheaf?
No, these equalities are as is. But what's going to follow? So the statement is that, here, let me put it this way. Stuka true of V tensor star with F is going to be the same as Stuka true of V tensor Schriek with F, but with a shift. And now I have to get it right. So if this were the constant sheaf, this would be too high, so this will be 2 times the order of the finite set I, the dimension of this x to the I. And then if you just sort of compare the formulas, that's going to imply that this Stuka I true of, wait, actually, shifts. Oops, sorry. No. Sorry, this is true. And then if I compare the formula defining this Stuka sub I of V, that's going to imply that this is equal to Stuka sub I of V shifted by minus 2 times the order of I. So in other words, by Jouet's theorem, our construction is not, it's non-trivial to say that it coincides with the usual construction up to shifts anyway, but it does, so it's okay. And one other thing I see that I just sort of want to record for a moment is, in particular, these objects that come from my functor are Lee's sheaves. Yeah, I should say, when you prove this exercise, I had said something about tensor Schriek before, and that's where you'll use this kind of ULA-ness property. Okay, so that's sort of the major stuff I have to say right now about this Stuka's functor and how I want to think about it. So now I want to kind of go back to these spaces of restricted and arithmetic local systems. So first, so the kind of tool here is that there exists a canonical functor we call localization. G-check run to the space of quasi-coherent sheaves on this locsys G-check restricted. This is a canonical symmetric monoidal. The kind of idea, if you want, for me, is that if you take like an I tuple, let's say you have some bunch of points inside of the curve, some bunch of representations, and you also have some local system. This is going to give rise to a vector space, which is somehow you take your local system, you can twist it by each of these representations to get, right this way, V sub I twisted by sigma is going to be a certain local system on X. So by its nature, whenever you have a representation, you get at least, and a local system, you get at least sheaf on X. Then I can take the fiber at this point xi, and I can tensor from I equals 1 to n.
In the beginning, you said you also work with InCode-Nope. So do you really mean QCO here for the sake of exposition? No. You literally mean QCO.
I literally mean QCO, yeah.
Okay, thanks.
Okay, so I have this vector space, and sort of kind of properly, the way I should say this is that there's a canonical functor by definition from rep G-check. So just remembering the definition, there's a canonical functor from rep G-check to these sheaves on X tensor with quasi-co Loxus G-check restricted, which I think of as some kind of universal version of this kind of construction with a single point. And so this is, remember, just whenever I had a scheme or whatever, I can put that S here, and I'm taking the identity map from Loxus G-check restricted to itself. So this gives me this kind of data. And then I can take, there we go. Put it here. So I can then tensor up to get a functor from rep G-check to the I to least sheaves on X, tensor I times, tensor quasi-co of Loxus G-check restricted.
We cannot see.
Which then I can map here by taking exterior products of my local systems. And so I don't know how to write it. And then, what I'll do is on the second factor is I'll just tensor up overall all of these I tuple factors, just like the symmetric monoidal functor on the symmetric monoidal structure on quasi-co. That's what I'm using.
What is VI comma sigma?
Yeah, so what I mean is like, what kind of thing is sigma when I say a G-check local system? So for me, it's a tensor functor from rep G-check to least sheaves on X. And it's like, evaluate that tensor functor to get a least sheaf on X. So you take your representation and your local system that produces for you a least sheaf.
Thank you.
So like, if this is GLN and this is some you think of a local system in the usual way, some rank n thing, and maybe your representation is some symmetric power of a standard representation, this will be the symmetric power of that standard, of that local system you were thinking about. So I get something like this, and then like before, I can, this is going to give rise to a functor from rep G-check the I tensor with sheaves on X to the I to quasi-co Loxus G-check restricted by sort of using my sheaf on X to the I to integrate out the least sheaf here. And as I vary my finite set I suitably, this will give me, so this is sort of by definition, this is going to be loc composed with this insert some I. Why it's called localization, it's like, the idea is that this gives you a tool to study quasi-co of Loxus G-check restricted in a way that's somehow more local on the curve. Sorry for this shadow. I don't know what to do about it. Okay, so we then have a theorem, which I'm just going to give a precise reference to it, although it's not quite what you might necessarily want. So references our third paper, corollary 2.3.4. And I'm saying that this is a slightly immoral reference because all of the hard work happens in the first long paper, but this is, well, this is where it's explicitly stated. So you would trace a bunch of references if you looked here. So the assertion is that a functor f from rep G-check run to vector spaces factors and factors uniquely as in the following way. So going to be that here I have my f, here I have my localization. Enhanced, if and only if a certain concrete condition holds, for every finite set I, the functor f sub I from representations of g check to the I to sheaves on x to the I takes values. So this was something I defined previously associated to this kind of data, takes values in these on x to the I. So the picture you're supposed to have is that somehow these quasi-coherent sheaves are really some kind of, they can be explicitly described in terms of rep g-check run and this functor of localization. So this localization you should think of as somehow surjective. It's kind of quotient functor, and the what do I want to say? Like somehow there's the kernel has some kind of very, in some sense, explicit nature, or the image of the kind of dual functor. There's also like a related dual functor that's fully faithful from here to here, and it involves basically functors from rep g-check to the I to leads on x to the I. Yeah, and so I guess.
Should we think of representations on g-check run, rep g-check run as something like sheaves on the space of all possible collections of Satake parameters, and then you're telling us which of them are automorphic?
Not, well, it's not automorphic, but which come from some kind of global data, right?
Yeah, okay, yeah. Which of them factor through Galois?
Yeah, that's exactly right. I should say like, yeah, I mean, like the kind of context for this sort of statement is like sort of standard in like the world of like topology and vertex algebras and this kind of thing. Like there are these kind of local to global principles where if you work over this like Ron space, you consider all sorts of configurations and you think about some sort of local data, but again, you work purely over Ron, then it happens in a lot of circumstances that you get kind of global output from this sort of circumstance. So maybe let me not say like, so sometimes like in over complex numbers, for instance, like some kind of vertex algebras, which are some things that involve this Ron space, just purely locally can give rise to things involving like the space of G bundles. When you take, again, when you work over all of Ron. And so this kind of principle, it's ultimately derives from those kinds of ideas. But yeah, it exactly gives sort of an explicit statement for like, it's in some sense like a very explicit geometric statement that says like, if you have some kind of huge Hecke algebra acting, what do you need in order for it to factor through some kind of global information, global Galois information? And the answer is you need to have extended that to Ron space. It doesn't make sense arithmetically. And then you just have to check some concrete condition. So a corollary is that there exists a functor Stuka enhanced from quasi-co of Loxus G-check restricted to vect. So this is corollary of Jouet's theorem. And it's kind of characterized by this diagram. And sort of generalities are going to imply that Stuka enhanced epsilon of sheaf F is going to automatically be given by some kind of because of the formal nature, I have to say it's like compactly supported global sections or INDCO global sections or something like this. It's kind of could ignore it at first pass. Looks this G-check restricted. And then I'll tensor with a certain sheaf called Drinfeld geometric. Sorry, this is a Drinfeld geometric for some uniquely defined Drinfeld geometric in quasi-co of Looksys G-check restricted. So what you should think is that this, well, what's true is that this Drinfeld geometric actually comes from push forward from a certain object on this arithmetic local systems. So that would be like the true Drinfeld sheaf. Let me just say the kind of, I don't want to spell this out at the moment, but you can just sort of by hand descend this sheaf to Looksys arithmetic using the partial Frobenius structure on Stuka cohomology. So it's sort of, I was saying that somehow these one equivalent version to this picture, not obviously equivalent, but it's that quasi-coherent sheaves on Looksys G-check restricted are equivalent to compatible systems of functors from rep G-check to the I to Lees of x to the I for all finite sets I, suitably compatible. And if you just replace this with Vey sheaves over here, you get sheaves on, sorry, like the I tuple version of Vey sheaves, like Vey along each factor here separately. Then, well, by Drinfeld's lemma and general kind of stuff, that's going to be equivalent to a sheaf on this Looksys G-check arithmetic. And so that turns out to give you exactly the data you need to descend this. I'll give kind of a different discussion of it in a little bit that will also give that sort of descent. But one basic property of this Drinfeld sheaf is that kind of by construction, its global sections are compactly supported automorphic functions.
Can you move it a little bit?
Okay, so now a claim I want to make is that, a little informally, is that geometric Langlands predicts. So I'm going to just pretend that this Drinfeld sheaf exists and not worry a ton about what I've literally said versus what I've I should have said. And part of it is, okay. So this assertion, so what I claim is that geometric Langlands actually predicts for you that this Drinfeld sheaf is the dualizing complex on the space of arithmetic local systems. So, should say, this is a push forward of Grams and quasi-co. Looksys G-check. In other words, what I claim is that geometric Langlands gives you a way to calculate this sheaf completely explicitly. And so in some sense, let me just say the picture you're supposed to have is that if sigma is this is like elliptic or discrete, whatever you want to call it, then so I should say Xin-Wen also stated this in his talk. I sort of want to explain how we derive this prediction. So the picture is that if you have a sort of elliptic or discrete parameter, you can take its automorphisms, take its classifying stack, and this is a connected component of this Looksys G-check arithmetic. which somehow is much nicer. It's not formal and so on. It's just, I should say, serious J2 kinds of things. So, let's say, well, so in this case, this is in particular smooth, and so the dualizing sheaf is going to equal the structure sheaf.
Sorry, what was the definition of the Drinfeld sheaf on the arithmetic local systems?
Yeah, that's what I was saying, that I sort of am going to elide for the moment. So I'll give it some descent data by a different construction in a little bit, but the assertion, which unfortunately is hard to actually tease out from our papers because of just, I don't know, human frailty. So the assertion is that giving a sheaf on this Lhokstis G-check arithmetic is going to be the same as giving a bunch of functors from here to here for these V sheaves. And the claim is that really that's what Stukas give you, not V sheaves, but like this I-tuple version of V. It's V along each factor. And that's what partial Frobenius gives you classically. And then Jouet gives you the Leibniz. And so you do get some sheaf at the end of the day.
And then what is the statement about push forward? Push forward.
So the relationship between the two constructions is that this object is the push forward of this Drinfeld sheaf. So you can map the space of V parameters to the space of geometric Langlands, geometric like local systems with some forgetful functor. And the claim is that this sheaf I honestly constructed up here really comes from something supported on the arithmetic or pushed forward from the arithmetic locus. I'm just going to sort of ask you to take that on faith for a moment, I've made a precise statement about what it is, but I haven't given 100% of the details on it.
Okay.
That's my claim. So the claim in this case is that what we're going to see is some kind of like one-dimensional somehow giving a one-dimensional summand of the space of automorphic functions on G of FQ. Let me just suppose that the group is semi-simple for simplicity. So this group is finite by assumption, and so omega is its constant sheaf, and so it's sort of computing, so to say, invariance of the trivial representation for some finite group, characteristic zero coefficients. It's just something one-dimensional. But then in general, somehow the picture is much messier near like the trivial representation, for instance, which is not a surprise, is like Langlands always gets kind of messy near the trivial representation.
But Sam, sorry, just to clarify, what we told us before is a theorem. The claim is for now a prediction.
What I said before is a theorem. The claim is, well, this is a provable claim, but it's that if you assume a version of geometric Langlands conjecture, then you'll deduce this. And this is sort of the resulting picture that you obtain.
But the previous is not, what we saw before does not rely on any geometric Langlands conjecture.
Correct, yeah. No geometric Langlands has appeared. It's related to Tom's question earlier. Do I mean INTCO nilp? No, I haven't talked about geometric Langlands, which is where that comes in.
Okay.
Yeah. But so far, everything's sort of unconditional, and oops, I just messed up my notes. Everything's unconditional and so on. So and it didn't it only required you to know Hecke functors, and it didn't require you to know more, in some sense. We see the ingredients of geometric Langlands here. There's some sheaves on Bun-G, and there's some space of local systems, but somehow the point is that in order to really compute this Drinfeld sheaf, like from what I've told you before, there's no, it's hard to get a feeling for it, right? In the way that like it's hard just using like, I mean, Langland's philosophy can say a lot about this space, but it can't tell you somehow like exactly what it is supposed to be. But what we're saying is that this space should be global sections of this particular sheaf on the space of arithmetic Langlands parameters. And that's hard to deduce just without, it's hard to deduce a conjecture like that without more information somehow. Okay, so that's the goal. So let's be in the geometric setting. So in other words, what I want to do is give this claim, and then first I should tell you what geometric Langlands conjectures say here. So there's a certain nice subcategory that we call sheaves with nilpotent singular support on Bun-G. And this lives inside of the world of all sheaves on Bun-G. So for instance, when G is abelian, this is just the category of local systems like Lee's sheaves on Bun-G. In general, it's something. So as far as I know, I think Lamone was the first one to sort of think seriously about this kind of thing, but maybe it was Drinfeld. And there's a sort of old philosophy that, like, for instance, Hecke eigensheaves should live here. And yeah, and this category was defined, like the world of singular support for étale sheaves wasn't defined until a few years ago by Beilinson, and the theory was developed a lot further by Saito. What nilpotence means, you should think of it as like good, or what singular support means, you should think of it as sort of good properties with respect to vanishing cycles. Like if you're on a smooth variety and you take a local system and you take any function, then its vanishing cycles are going to be 0. And that's reflecting the fact that its singular support is as small as possible. Whereas if you took a skyscraper sheaf and you take any function, it is going to have vanishing cycles, and that's going to represent the fact that its singular support is as bad as possible. So it's some kind of measure of the sheaf. And in fact, one of the main parts of our work is just sort of like giving a different picture for this sheaf's nilp, but the notation stuck around. And I'll explain that different picture in the next 6 minutes, I guess. So, so what we conjecture, so this is the version of geometric Langlands that's relevant here, is that this sheaves nilp on Bun-G is equivalent to what I said in the beginning of the talk, sort of Chekhov's gun here, this INTCO, and then there's some spectral version of this nilp condition that appears, Oxis G-check restricted. The role of this nilp, it's also appears in the Betti-Langlands. It appeared originally in the Betti-Langlands program of Ben-Zvi and Nadler, that Nadler and Yoon have been working on with great success in recent years. So it's not sort of our, I would say, main innovation here. Our main innovation is really the reasonableness of the right-hand side. But this is our conjecture. So when we, in our paper, we show that this kind of conjecture in characteristic 0, all versions of geometric Langlands turn out to be equivalent. This is the same as the D-module version. Well, it would be equivalent to the D-module version. It would be equivalent to the Betti version. And yeah. It's true for GM, it's true for P1. So this is what I'm going to sort of ultimately use. And to explain that, I need to kind of say a little bit more. So I want to say a little bit more about the structure of the left-hand side. So our main kind of object here is a certain weird object inside of rep gcheck run, which we call R, and we call it the Beilinson spectral projector. It's some object. Let me just say, let me tell you very briefly what it is. So it turns out, if you look at the definitions of this rep gcheck run, this turns out to be canonically self-dual as a DG category, since I've been using this tensor product throughout. Let me just say out loud, I'm not going to write it down because it won't be meaningful to people who haven't seen it before and will be meaningful to people who have. So if you just take, this was defined as some kind of colimit. So it's dual, you would expect to be a limit, the dual categories under the dual functors. If you look at this particular situation, those dual categories are the same as the original categories. Those dual functors are the right adjoints of the original functors. And a limit under right adjoints is a colimit under left adjoints by some favorite principle in this world. And so this guy's canonically self-dual. And so in particular, there's some kind of unit object inside of rep gcheck run tensor rep gcheck run. So it's something kind of like the regular representation, if I remove the word run here, as a bimodule. And then I can map this by identity tensor loc to rep gcheck run, tensor this quasi-co loxis gcheck restricted. And then I can do identity tensor this compactly supported, essentially global sections on the right-hand side, rep gcheck run. And by definition, the resulting object is this R. And so what this formula means, it's kind of explicit, it's kind of inexplicit, it's a little abstract. That's the state of things. But this is some kind of lovely object. And let me say, it's of global nature. I really used this localization functor. So it's like I don't know. It's something, in some sense, if you lifted it to here, something that represents this localization functor. So it's an object that lives in some local world, but carries some global information. Maybe that's the right way to think about it. And let me say that we calculate in our first paper that this, sorry, was that?
Yeah.
This loc of R is O of the structure sheaf of this loxis restricted. So if you take this object, you can then further localize it, you're going to get the structure sheaf. So it's something kind of universal and kind of global nature. And so we show that the functor from R star from sheaves on Bun-G, so this Hecke functor defined by this local object, maps into sheaves nilp on Bun-G and gives the right adjoint to the embedding. So a consequence of that, which might not obviously be a consequence of this, but it's pretty close, is that in some sense, an equivalent formulation is that this sheaves nilp of Bun-G turns out to be the maximal subcategory of sheaves on Bun-G. so that this ref G check Ron acts through quasi-cove Lioxis G check restricted. So in other words, it's that same sort of surjectivity principle I said before. You can like kind of take this Loc functor, take its kernel, in some sense, some kind of tensor ideal, and the annihilator of that tensor ideal is exactly this Sheaves Nulp. For time reasons, I'm gonna write less stuff down. So a kind of application of this, sort of essentially this exact idea, is that if you're given an object K instead of sheaves on bun G times bun G, so think the kernel of some functor, this is going to give rise to, I should say, maybe I should also say this kind of stuff, we used to give a bunch of structural properties about this sheaves nulp on bun G. So for instance, it plays well with these categorical tensor products. I'm not going to say it explicitly. So this is going to give rise to a functor from sheaves nulp on bun G. So then I can take this to sheaves of bun G. I can apply like the functor attached to my kernel. Well, I guess I'll write it as f sub k. And then I can do this R again to get back down to sheaves nulp. And let me call this just laziness f sub k sub nulp to mean like it's the functor you get from here to here from that kernel essentially. So then the kind of theorem, which is the main content of our second paper, is that the abstract categorical trace of this functor, this f sub k of nulp. So let me just say for a moment that if you have some suitable DG category, it should be what's called dualizable, which makes sense in this context, and you have some endofunctor of it, you can take its trace to get a vector space. This is related to Hochschild homology and is a sort of abstraction of the discussion we had earlier about geometric trace. They're cousins. This is putting them on a closer relationship in this situation. So we show that this trace of f sub k of nulp can be computed as the geometric trace of, I'm going to write R composed with K composed with R. I don't really know that this is the best notation, but here's what and this is also just the geometric trace, like R composed with K. So what I mean here is the following. This K is a sheaf on bun G times bun G. I said this has this monoidal structure. And so on the other hand, this R is a Hecke functor, so it really kind of defines for you, maybe it would be better to write like K sub R here. Sorry, it's too small, but I mean, like, think of that Hecke functor as an object on bun G times bun G, as that kernel that I wrote before, and just compose them. And this R kind of squares to 0 by this idempotence property. And so if I move the factors around, you'll see that like the fact that it's a sort of projector makes this a kind of standard manipulation here. And so this is, this is right. So this is the assertion. The categorical trace of this functor is going to be the actual, the geometric trace of this somehow functor defined by the kernel. Which now has the nice property, like it has the sort of application that I can think about, like this categorical Langlands conjecture is something about actual traces on, it's something about actual DG categories, and that's like all I have access to. I don't have like the sort of geometry that went into this trace geometric. But a corollary that we show, sort of immediate corollary of this identity, is that the somehow the trace, so let me say, for V object of this source of Hecke categories, the trace of this corresponding functor from Sheaves Nilp on G to itself, abstract trace, is going to be the geometric trace of, oh, and sorry, I want to also compose with, I'm going to do a Frobenius pullback. Sorry that it's getting messier. So I apply Frobenius pullback, and then I do this trace. This will be the geometric trace of sort of this R composed with like K sub V, if you want, composed with like identity times Frobenius upper star, which is the geometric trace of, I said this K construction is monoidal, so it's going to be this R sort of multiplied by my object V, composed with this identity Frobenius upper star thing. And this was by definition Stuka of R star V. So in other words, if I take some object of rep G check run, I can then compute its trace, the trace of the corresponding Frobenius twisted Hecke operator in terms of my Stuka construction. First, I have this weird object R, I multiply by it, and then I take Stukas. Now, the nice thing is that this, I'm going to do something kind of non-trivial now. So this I can express in terms of my Stuka enhanced using the symmetric monoidality of this localization functor. This is the structure sheaf, so tensoring with it does nothing. The Stuka enhanced of loca V. And finally, this is Stuka V. So what we see is that categorical traces of sort of Frobenius Hecke operators give rise to, oh, and this is, I should say, on Sheaves Nilp, give rise to Stuka homology. And let me just say one kind of particular case. So when V is the like trivial representation here, it implies that the trace of Frobenius on G acting on Sheaves Nilp on G is equal to compactly supported functions, in other words, automorphic forms. It's not hard to show. Again, it's written as a conjecture in our paper, but it's the trace of the kind of operator phi acting on this INTCO spectral Nilp, Loxus G check, is going to be the trace of, so I'll comment on this in just a moment. It'll be the same as this is restricted. It'll be the trace of the Frobenius acting on this INTCO Loxus G check restricted. This is just sort of functoriality of geometric Langlands for automorphisms here, for this Frobenius. So this will be this term, which by generalities is Loxus of arithmetic, the fixed points under this operator with coefficients in its dualizing sheaf. So if you believe in geometric Langlands, then you believe this is equal to this. Let me comment very briefly about these two things. So the reason this kind of thing works is that if you take some local system with a Weil structure, you take one of these, what we call like geometric Arthur parameters. So it's kind of a class in H2 of that local system twisted by the adjoint representation. And you want that to match up under this so it's for sigma, and it should be compatible with the Weil structure. In that case, that class in H2 is sort of automatically nilpotent. The H2 is the same as H0, in this context, and any such endomorphism is going to be automatically nilpotent. So maybe I won't explain that in detail because I'm already 10 minutes over time. So that's what I wanted to get through. So thank you. I'm sorry for going over.
Thank you, Sam. Let's start with questions.
Okay, so considering the title of this talk, so if I'm a number theorist, what do I use this for? I guess I don't see, so we did all of this work, we have this geometric setting, but it seems like if we take trace of Frobenius, we just recover the initial setup. What do we get out of it that we didn't have before?
Well, can you say the last part again?
Just what do we get from the setup that we didn't have before?
Yeah. So, So here's the picture that I see at the end of the day here. So I thought that arithmetic Langlands was about compactly supported functions on Bun-G of FQ. Arithmetic Langlands everywhere unramified over a function field. And then what I learned was that if I think in those kinds of terms, things get kind of very, very messy. So you have the Hecke operators, and maybe you consider mutual eigenfunctions, but there are going to be sort of multiplicities that appear when that happens for groups besides GLN, and also like which systems of Hecke eigenvalues are supposed to like behave well. It's not always super. It can be a little bit somehow rough. And at the end of the day, when you think like, what does the space of automorphic forms actually look like? It's, the traditional picture, it can be quite inexplicit, I think, because of, because of L packets, because of Eisenstein contributions, and so this is saying that there's another way of thinking about this, which is that what you're supposed to look at is not actually a vector space. It's not actually the space of automorphic functions. That actually is a shadow of some kind of richer object, which is a certain sheaf on the moduli stack of Langlands parameters, this Loxus arithmetic, and that sheaf is something, and that should be somehow the case, I would say, in general. And that sheaf is something which is a richer object with more information and is much somehow more likely to be describable in terms of like, if you want to say like, what do automorphic forms look like? That sheaf is really the thing that you want to describe. It's not going to be the vector space of automorphic forms, but the local thing is going to have a better description. And of course, in nice cases, things should be somehow, you consider many Langlands parameters that are isolated inside of the moduli space. And so that's why like the cuspidal theory works well, but you can't live your whole life in the cuspidal world. So that's kind of my answer to that question. So this is telling you what automorphic forms for a reductive group look like in a certain case. It's not saying, I never said the word L packets. I never said anything about functoriality. It's just like, this is it. This is what the vector space is. And that's, it's, well, there's a lot to imagine about what that could look like in a number theoretic context. It's very somehow, I would say, dreamy at the current moment, but I don't know. Does that answer your question at all? Maybe it was unconvincing.
Is there anything concrete that you could like that? So from this perspective, so there's a lot more machinery available in the geometric setting. Is there anything like really concrete that you could get out of that can't be shown just from the possible interpretation?
I have.
This inequality is extremely concrete if you think about it. On the left, on the top, you just have the automorphic forms you care about. On the bottom, you have some rather explicit algebraic stack that you can actually compute in practice more or less. You have a completely explicit G on it and just take over section. That's it. It's a super concrete thing.
Do you get a description by doing that computation other than the space automorphic form?
No, it's a super different thing. It's purely on the dual side. It's completely on the dual side. So basically, we have all these descriptions that if you look at the space of, I don't know, discrete automorphic forms, it should be a direct sum over whatever also parameters of some specific stuff. And it's all in this formula. And if you just sit down and make this formula explicit, it should all just fall out of it. Which actually brings me to my question, how would actually ASA parameters arise out of this?
So that's so it's addressed to some extent in the paper. So the answer is that it's somehow supposed to be related to like this difference between INTCO and quasi-CO and this nilpotent thing and what you're.
But this is, I mean, in the final line, there is no more nilpotent support, whatever. Right? It's just.
Yes, that's right. Yeah.
Like,
okay, maybe.
Like this final line is just about representation of the wave group. There's no extra SO2 anywhere. But suddenly the ASA parameters must sum up for all of this still.
So,
yeah, go ahead.
Yeah, I think one needs to do a little bit more to, like, on this stack, we have described the functions of excursion operations. Like you need to somehow probably describe really how the, like the Galois homology like work.
Yes, I mean, yes, to make it a useful statement, you somehow need to know that this is somehow compatible with the action of vector operator or something like that, to know that automorphic form and this is point where it sits on the stack of L parameters there that they correspond. But okay, let's leave that. But independently of this,
so, yeah, I mean, okay, let me say something vague about it, which it's not the part I've thought most about. But so what you're saying right there about like usual Hecke operators, that's built into the construction. Like this, I mean, maybe I could be a little bit more explicit about it, but like the sheaves of Bungie, as I said, it has an action of quasi-CO of Loxus G check and so on at some point. And the equivalence I wrote down should be compatible for that thing. You can really essentially write down a functor and say properties about it. And this is what's supposed to happen. So it's the functor I would write down has that property. So then it's definitely going to be compatible with usual Hecke operators. So the thing that I don't the motto that other people have thought about more than me is that Arthur parameters come up when you consider the compatibility for derived geometric Satake. So it's not just like at a point, it's not just the rep G check X here, but the equivariant derived category of GEVO invariant sheaves on the Grassmannian X. And this is, again, sort of something you can do over Ron space and so on. And it encodes information like that sort of action is what you use to geometrically pick out what's supposed to kind of correspond to quasi-CO under this equivalence. So it picks out things like temperedness.
But these other parameters arrive before you consider a Hecke action. You thought they're just a discrete part of something.
So maybe you could explain why the parameter for the trivial representation appears discretely on the bottom line. Is that a good question?
That's probably a good question, yeah.
Where can I see that the trivial representation contributes discretely on the bottom? Is a direct sum of the bottom. Does this have to do with singularities and something? Is it hiding in the dualizing sheaf?
All right, you're asking good questions, and I have to think about it offline.
So I guess actually,
Xinwen wants to.
so I didn't calculate this example, but for modular curve, can do something similar with level. What happens is on this, there's a part with the trivial representation, but the stack is not trivial. So there's still some sheaf on it, the non-trivial things support everywhere, but after you take the cohomology, it become one-dimensional trivial, or maybe 1 plus cycle 4. Appearing H2. And also H1, if you the modular curve is non-compact.
But do you have some general philosophy how other parameters would arise if we just try to compute these global sections?
Yeah, maybe discuss later.
Yeah.
Yeah.
Yeah, maybe. Can I also?
Should we let the students ask some questions or? Okay, go ahead.
Yeah, actually, just one question. So, I guess Drinfield's lemma also still plays a role.
Yes.
Do you locate exactly in Tongxue's work or somewhere in your work you also use it?
Use Drinfield's lemma?
Uh-huh.
Okay, so okay, so I think that probably the state of our papers, if I'm being honest, is the following. So there's an assertion that I made that is implied by them, but is not explicitly stated, which is that the data you need to define a quasi-coherent sheaf on the space of arithmetic Langlands parameters is some kind of compatible system of functors from these rep-G check to the I to these sort of termwise Lees sheaves on X to the I. And what would naturally actually appear in the statement of that theorem is the tensor product of I many copies of that category. So you sort of need to know that the thing you're producing can be written as a co-limit of things built out of exterior products from the two factors. So it's a consequence of Drinfield's lemma that those two things are the same. So if you want to do this for, so somehow honestly construct this Drinfeld sheaf, that's where you run into it, is that a priori you constructed this Weil sheaf on whatever, I don't know the term for it, but like this I-fold Weil sheaf on X to the I, but you really need to know that it came as an exterior product of things from each factor. The alternative kind of hack that I didn't quite write down is that this kind of expression actually, so when you have basically this quasi-co of log-cis acting here, so it's some just monoidal category acting here, it's got some dualizability properties, you've got some endofunctor of the module category compatible with some endofunctor of the base. That's going to automatically, by like Hochschild homology formalism, give you that this trace upgrades to an object of the Hochschild homology of that monoidal category, which in this case is quasi-co of log-cis arithmetic. So in that sense, it's actually true that you can avoid Drinfeld's lemma if you want to use this construction of the Drinfeld sheaf. Somehow it doesn't, just the nice properties of this category or something encode somehow purely formally the Drinfeld lemma thing. I mean, my collaborators, Gates-Goy, Kazhdan, Rosenblum, Varshavsky wrote a paper before ours where they call it Toyd model for Drinfeld Stukas, I think. And the idea was to sort of just pretend like all of the categories of sheaves behave super well and somehow give a topological version of the story. And what they observed is that you sort of naturally end up with a quasi-coherent sheaf on the somehow space of arithmetic Langlands parameters in their toy model, and that sort of data is automatically going to carry a bunch of partial Frobenius kind of operators. And so it refines that construction in the sense.
Okay, one short question. Can you describe the connected components of log-cis arithmetic? Or the description of that?
Yeah, it's a great question. And as far as I'm aware, no. I would, it's a very, it's a very naive question, and I do not know the answer to it. So
Naive, you mean
it's
natural?
there's some restriction, which is that like, wait, what was the comment?
You said it's a naive question, but I think you meant the natural question.
Well, it's a very natural question, but I mean, not even in the sense like connected components. How bad could it be? But it's something very coarse about the geometry of a space, and of course, it can be really non-trivial in a lot of examples. And as far as I know, it's not easy to answer in this case. So, I mean, what we say about this restricted space gives some kind of condition. So, when you consider kind of like the geometric, the semi-simplification of the underlying geometric Galois representation can't change in connected components, but it's obviously it's a much finer decomposition than that.
So maybe that's premature given the previous answer, but can you prove that Lox's arithmetic is naturally defined over Q and is independent of L, given the existence of convention?
Yeah, it's again very natural question. I wouldn't think it's yeah, I can't do it.
Can you explain about I guess you have done that, but can you explain again the meaning of nil here? So the condition of nilpotent, and how in the step you can remove this condition?
Can we remove this condition? Is that what you're asking?
Yeah. First of all, what does it mean then?
Yeah. So this nilpotent condition. Okay. First of all, you can think about it for me from 99.9% of the things that we did in this paper. It's much better to think about this kind of in terms of the Hecke action. And it turns out that actually what these objects are the ones where when you apply this Hecke functor along the curve X, you get something which is locally constant along that curve. That's kind of full stop what the answer is. So it's just like in the case of GM or something like that, like there are Hecke operators, just some translation by some kind of divisor or point or something like this in Bun GM. And so that like clearly, if you run that kind of construction for something like a skyscraper sheaf, you're not going to get something locally constant. Like the fiber, you just translate from one point to another, and it's not locally constant. It was only at the somehow marked point. And so this is encoding a posteriori a very similar kind of idea. These are the objects, and maybe let me just say, in the Bun GM case, the objects that do have that property are just the local systems. The local systems, you translate them, it's locally constant along the points as you're translating different points. This is a somewhat subtle formula that expresses the same idea in the non-abelian situation. So for instance, well, these turn out to be exactly the sheaves where when you apply a Hecke functor, you get something locally constant along the curve. This is one of our theorems. We call it converse to Nadler-Yun theorem. They show that objects here have that local constancy property, at least in the topological situation. And we show that conversely, any object with that property actually has a nilpotent singular support. So it's a kind of, for me, it's a kind of subtle characterization of what these objects look like. I think there's stuff to say about it, but that's for me the way I think about this condition. And properly, it's again sort of for Bun GM, only 0 is nilpotent. And the basic principle of singular support is that 0 singular support, so singular support of a sheaf in general, it's some subset of the cotangent bundle of the ambient space. Let's say you're on smooth variety. And having singular support the 0 section means that you're a local system is the basic principle. And somehow picking up bigger and bigger cotangent fibers is saying that you have like worse variation in some directions. Maybe you're like a local system in this direction, but not in that direction. Imagine like a constant sheaf, but pushed forward from some subvariety. And it's a kind of subtle business a little bit, but that's the kind of thing it is and the kind of thing that it's telling you in this situation.